In this video, we discuss certain terms associated with random processes, namely the mean, correlation, and covariance. Now, what is mean of random process? The mean of single random variable is given as, suppose a single random variable is x, then its mean value is defined as mu x is equal to ex, that is equal to integral minus infinity to infinity x fx x dx, and this quantity is fxx is the PDF. The same formula can be given to the random process also, but here the random process is denoted as xt. And what is random process? In the random process, the sample space is mapped to the time functions. Therefore, here at time t, the random process gives us a random variable at time t. Now, if I want the mean value of xt, that is given as mu xt is equal to expectation of xt, and that is equal to integral minus infinity to infinity x fxt x dx. This fxt x dx is probability density function of the random process at the time t. Suppose if I want the random process at time is equal to t1, then it becomes xt1. So in that case, the mean value is mu x t1 is equal to expectation of x t1, and that is given as integral minus infinity to infinity x f x t1 x dx. So here the fx t1 x is the probability density function of random process at time t is equal to t1. So in general, the equation for mean of random process xt is expectation of xt, that is given as integral minus infinity to infinity s fxt x dx. We have seen what is mean of random process. ext1 gives us the mean value of random process at time t is equal to t1. Similarly, ex2 is mean value of random process at time is equal to t2. Now I'll draw a simple diagram here to denote the random process. Suppose these time functions are constituting the random process. We know random process, in random process the sample space is mapped onto the time functions. Now if this is random process and at time t1, I draw it with a red line here, this is time t1. At time t1, these points constitute one random variable taken as xt1. Similarly, I'll take another time t is equal to t2. So at this time t2, these points or these values constitute another random variable x t2, and so on. If I take suppose t3, at t3, x t3 constitutes another random variable. Now if I find mean of this, that is given as ex t1, and suppose if I take mean of this value, that is marked as ex t2, and so on. So in general, the mean value at time t1 and time t2 and time t3 may be different. They are function of time in general. But there is a specific condition in a random process. Suppose in a random process, at time t1, the probability density function time t1 is same as the PDF at time t2, and so on. Then that random process is known as stationary to first order. So in any random process, if the probability density function at time t1 is equal to the probability density function at time t2, then that random process is known as stationary to first order. This is very important term associated with the random process. For a stationary random process, we have seen that the PDFs at different time epochs are same. That is, fx t1 x is equal to fx t2 x is equal to fx t3 x and so on. So the PDFs at different time epochs are equal. In that case, we already seen that mean value at t1, that is mu x t1 is equal to mu x at t2 and that is equal to mu x at t3. The PDFs are same at different time epochs, that their mean values are also same. Therefore, we can say that the mean value is independent of time. It is constant at all time epochs. So for all t, mu xt is equal to mu x. In the case of stationary random process, it is also known as stationary to first order, as we are considering the mean value. Now another important term associated with random processes, that is autocorrelation function. To understand autocorrelation of random process, we just consider the correlation between two random variables. That is, suppose if I want to see the correlation between random variables x and y, then it is denoted as exy. That is given as integral minus infinity to infinity and integral minus infinity to infinity xy f x y xy dx dy. This fxy xy is joint PDF. Now the same definition can be adapted to get autocorrelation of random process. Now in the random process, suppose xt is a random process. Then at t is equal to t1, we have one random variable xt1. At t is equal to t2, we have another random variable xt2. Now, if I want to find out the correlation between xt1 and xt2, that is given as expectation of xt1 and xt2, same as this. Now, as per the definition, it is double integral from minus infinity to infinity x1 x2 fxt1 xt2 x1 x2 dx1 dx2. The whole thing is joint probability density function. So this particular function is known as autocorrelation function, denoted as Rx t1 t2. R represents autocorrelation function of random variable x between time t1 and t2. Why it is known as autocorrelation function? Because we are getting these two random variables xt1 and xt2 from the same random process. That is why it is known as autocorrelation function. We rewrite the equation for autocorrelation function here. That is Rx t1 t2 is equal to expectation of xt1 and xt2, and if we expand this with double integral minus infinity to infinity, we have x1 x2 and we have fx t1 xt2 x1 x2 dx1 dx2. Don't worry with the notation here. If we understand how to represent joint PDFs, this would be evident. So xt1 is the random variable at time t1, xt2 is random variable at time t2. So the whole function denotes the joint probability density function. So this is for the autocorrelation function of random process at time t1 and t2. Suppose this joint probability density function depends only on the time difference t2 minus t1, not on individual times t1 and t2. Then that random process is known as the stationary to second order. We use the word second order here as we are involving two random variables xt1 and xt2. So if the joint probability density function fxt1, xt2, x1, x2 is depending only on the time difference, not on the individual times t1 and t2, then it is known as the random process is stationary to second order. Now in this particular situation, what would happen to autocorrelation function? In that case, the autocorrelation function Rx t1 t2 will be equal to Rx t2 minus t1. That is, the autocorrelation function depends on t2 minus t1. So in case if the joint probability density function is stationary to second order, then the autocorrelation function would become Rx t2 minus t1. That is, the autocorrelation function depends on the time difference of t2 and t1. We discuss autocovariance of random process. Firstly, we consider covariance of two random variables. That is given as expectation of x minus mu x into y minus mu y. So expectation of x minus mu x into y minus mu y gives us covariance of x and y. That is x minus mu x mean of x and y minus mean of y. The same definition can be adapted to understand autocovariance. In this covariance, from the random process xt, we are getting xt1 as random variable at time t1, xt2 is the random variable at time t2. In that case, the covariance, autocovariance, as these two random variables are taken from the same random process, we can use the term autocovariance represented as kx t1 t2 is given as expectation of xt1 minus its mean value into xt2 minus its mean value. The same definition is extended here. And if you expand this, we will get 4 terms. If we expand this equation, we will get 4 terms. And if the random process is stationary, in that case, we have that mu x mean value is constant for all t. Mu xt, I'll rewrite again here. Mu xt is equal to mu x for all values of t for random process. Similarly, for stationary random process, the autocorrelation function t1, t2 is equal to Rx t2 minus t1. These two results we have seen for a random process, stationary random process. So if you expand this equation and simplifying, we get the autocovariance of stationary random process as Rx t2 minus t1 minus mu x square. That is autocorrelation function minus square of the mean. So for a stationary random process, the covariance is given by, autocovariance is given by Rx t2 minus t1 minus mu x square x. It means for a stationary random process, the autocovariance depends on the time difference t2 minus t1 as it is in the case of autocorrelation. And one more important thing is the autocovariance can be obtained from its autocorrelation and its mean value. To compute autocovariance, we need to have only autocorrelation and its mean value. These are the two important points here. We discuss some important properties of autocorrelation function. I'll write it here again that for a random process, stationary random process, Rx t1 t2 is equal to Rx t2 minus t1, depends only on the time difference if it is a stationary random process. Suppose if I mention t2 minus t1, that is the time difference, as tau. And in that case, we can rewrite the equation for autocorrelation as Rx tau is equal to expectation of xt plus tau and xt for all t. You can observe the time difference between t plus tau and t is tau. So we can alternately write the autocorrelation function for stationary random process this way. Now in this equation, if I put tau is equal to 0, then this becomes Rx0 is equal to expectation of x square t. Expectation of x square t is nothing but mean square value of random process. So at t is equal to 0, the autocorrelation function is giving us the mean square value of random process. This is very important observation. The second property of autocorrelation function is that it is an even function of tau. So we can write Rx tau is equal to Rx minus tau as an even function of tau. Now this can be reduced readily from this equation. The autocorrelation function can also be written as expectation of xt x of t minus tau. So the time difference between this and this is minus tau. So from this equation we can write that Rx tau is equal to Rx minus tau, that it is even function of tau. The third property is the autocorrelation function has its maximum magnitude at tau is equal to 0. Suppose if I substitute tau is equal to 0 in the equation, then modulus of Rx tau is always less than or equal to Rx0. It means that tau is equal to 0, it has got maximum value, or less than 0. Its maximum value is equal to 0 at tau is equal to 0. So these are the three important properties of autocorrelation function. Physical significance of autocorrelation function. From this diagram, the physical significance of autocorrelation function can be understood. Now we have seen that tau is the time difference of two time epochs, that is t2 minus t1. So the autocorrelation function gives us the interdependence of two random variables that are tau seconds apart. It basically gives us the interdependence of two random variables obtained at time t2 and t1, that is they are tau seconds apart. From this diagram, in the first curve, the variation in this autocorrelation function is very rapid with respect to t. Therefore, this is known as rapidly fluctuating random process. Similarly, in the second curve, with respect to tau, it is slowly varying. That's why this particular curve is known as slowly fluctuating random process. So this is how we can understand the interdependence of random variables with the idea of autocorrelation function. Now one particular term can be defined, that is known as decorrelation time tau 0. Suppose if I mark 1% of the total magnitude, total amplitude, approximately something like this, then for the small curve, this value is known as tau 0. For this big curve, this value is known as tau 0. So tau 0 is the correlation time at which its amplitude is 1% of maximum amplitude. It is indicated as tau 0. We discuss cross correlation and cross covariance. In the previous slides, we have seen autocorrelation. The autocorrelation function is given as Rx T1 T2 is equal to expectation of xt1 xt2. So in autocorrelation function, the random variables xt1 and xt2 are obtained for the same random process. Therefore, it is known as autocorrelation function. Now, if I want to write cross correlation, then we are obtaining the random variables from two different random processes. They are xt1 and yt2. So xt1 is obtained from the random process x at time t1. Yt2 is obtained from the random process y at time t2. Now the cross correlation is denoted as rxy t1 t2. Here x and y represents two different random processes. So rxy t1 t2 is equal to expectation of xt1 and yt2. This is the difference between cross correlation and autocorrelation. In autocorrelation, we are obtaining both the random variables from the same random process x. In the case of cross correlation, we are obtaining two random variables from two different random processes at time t1 and t2. And then the cross covariance. In the similar terms, we can define cross covariance as expectation of xt1 minus its mean value, yt2 minus its mean value. It is represented as kxy t1 t2. K represents cross covariance for random processes x and y at time t1 and t2. And then one more important result is that if the cross covariance is 0, kxy t1 t2 is equal to 0, then these two random processes x and y are uncorrelated. Now in this video we discussed about mean of random process, then we have seen what is autocorrelation and autocovariance, and for a stationary random process how the mean values and autocovariance and autocorrelation functions are changed. And then we also defined the cross correlation and cross covariance, and we also observed the physical significance of autocorrelation function.